Welcome back to another deep dive into the OEIS.
Yeah. Always a pleasure to be back.
We're getting pretty deep into this now.
This is fun.
This is fun. So we're going to be looking today at sequence A000150.
Okay.
And it deals with dissecting polygons into triangles.
Dissecting polygons sounds pretty straightforward, right?
Yeah.
But you know how it is with OEIS? There's always something a little bit more than meets the eye.
Oh, yeah. I'm sure there is. I mean, just looking at the title of the sequence, dissecting polygons rooted at an exterior edge and asymmetric with respect to that edge. I'm already like, wait, what does all that mean?
Right, yeah. So let's maybe start with a visual, right? So just imagine for a second like a pentagon, a nice five-sided polygon. Now imagine you pick one side of that pentagon, and we're gonna call that side our root.
Okay.
Right? And then we're gonna dissect this pentagon into triangles, but we want to do it in a way that's unique. And if you were to flip the pentagon over along that root edge, the dissection wouldn't look the same.
So it's like we're pinning it down on one side.
Exactly.
And then seeing all the different ways that we can cut it up.
Yeah, like all the distinct asymmetrical ways you can divide it into triangles.
Gotcha.
And that's what A000150 gives us. It tells us for any n-sided polygon how many of those unique dissections there are.
Okay.
And just to give you a sense of how this sequence starts out, it goes 0, 0, 1, 2, 7, 20, and it keeps growing from there.
Oh, wow. So it looks like the number of dissections just explodes as we add more sides.
Yeah, it gets pretty wild pretty quickly.
Yeah, and I'm already seeing here that this sequence has some really interesting connections to other math concepts.
Oh, absolutely.
Yeah.
It's a great example of how interconnected things are in the OEIS. And one of those connections is to something called Dicke paths.
Okay. As a number theory student, I'm pretty familiar with Dicke paths.
Yeah.
But how do they relate to cutting up polygons?
That's a great question. So Emmerich Deutsch, who's a contributor to the OEIS, he pointed out that A00150 is actually related to Dicke paths that have an odd number of peaks at even height. So remember, a Dicke path is like a path on a grid that never dips below its starting point. So think of it like you're taking steps up and down, but you can never go below where you started.
Right. Okay.
And so the way we dissect our polygon corresponds to a very specific type of Dicke path.
So there's like a correspondence between the dissection and the path.
Exactly. It's pretty cool, right?
That's a really unexpected connection.
Yeah, and there's even more. Jeffrey Kritzer, another contributor, he linked A000150 to unordered binary trees where the left and right subtrees are different.
Hold on. Now we've got binary trees in the mix, too. I'm starting to sense a third here.
Right. It's like all these seemingly different concepts are all intertwined.
Yeah.
And binary trees, with their branching structure, they offer another way to think about these polygon dissections.
Okay.
And that rule about the left and right subtrees being different, well, that reflects the asymmetry we're looking for in our dissections.
Okay. Can we maybe look at a concrete example of this?
Sure. Yeah.
Just to kind of solidify this concept of a rooted asymmetric dissection.
Absolutely. So let's take a simple example, just a square.
Okay.
Right. 4 sides.
Easy.
Pick any side as your root, doesn't matter which one. And now you can draw a single diagonal across the square to divide it into 2 triangles, right?
Okay.
And that's one valid dissection. But if you try to dissect it any other way, like using a different diagonal, you'll see that it creates a symmetrical dissection.
With respect to that root edge.
Exactly.
Yeah.
So for a square, there's only one unique asymmetrical dissection rooted at a side.
Okay.
And that's why the third term in our sequence is 1.
Okay. That makes sense now.
Yeah.
I'm even more curious about how these connections to Dicke paths and binary trees actually play out in helping us understand the sequence.
Yeah, we'll definitely dive deeper into those connections. But first, we should introduce another important player to the game, and that is Catalan numbers.
Ooh, Catalan numbers. Those are like the celebrities of combinatorics.
Exactly. They pop up everywhere.
Yeah, they really do. And they have a starring role in this, too.
They do. They have a very important role in the formulas for A000150.
I'm really curious to see how Catalan numbers tie into all of this.
Yeah, it's pretty fascinating. The formulas for A000150 actually involve the generating function for Catalan numbers.
Ah, generating functions.
Yes. Maybe for our listeners who might not be familiar with generating functions, we can give a quick explanation.
Yeah, that's a good idea. I mean, I know what they are as a number theory student.
Right. So a generating function is basically a really clever way to package an entire infinite sequence into a single function. It's like a mathematical suitcase that carries all the terms of the sequence inside it.
That's a great way to put it.
Yeah, so we're basically using the power of Catalan numbers packed into their generating function
Mm-hmm.
to help us understand these polygon dissections.
Okay.
One of the formulas that we have for A00000150, it was provided by Jeffrey Kritzer,
Okay.
and it expresses the generating function for A000150 in terms of the generating function for Catalan numbers.
Okay.
And it looks like this x times the quantity c of x squared divided by 2 minus c of x squared divided by 2.
So there's a lot going on in that formula. What is it actually telling us?
So basically it's saying that we can figure out the number of ways to dissect an n-gon by manipulating the generating function for Catalan numbers.
Okay.
All those squares and x's and dividing by 2, that's all part of the mathematical dance that connects these two seemingly different worlds.
It's amazing how we can use a tool from one area of math to unlock secrets in another.
Yeah, it really highlights the connections between number theory and combinatorics.
Absolutely. So we can figure out the number of dissections from this formula.
Yeah, we can use it to calculate those numbers.
Okay, cool. And how about the asymptotic formula? What's that all about?
Right. So if we want to get a sense of how quickly this sequence grows, as n gets really big, we can look at the asymptotic formula.
Okay.
And Vaclav Kosovic, he provided a really useful one. And it goes like this: a of n is approximately equal to 2 to the 2n minus 1 divided by the square root of pi times n to the 3/2 power.
Wow. Okay, so as the number of sides of our polygon, n gets bigger and bigger, this formula gives us an approximation for the number of dissections.
Exactly.
So what does this tell us about the growth of A000150?
Well, it basically tells us that the number of dissections grows exponentially as n increases.
Sure.
You see that the 2n minus 1 term in the numerator, that's what really drives that rapid growth.
So the more sides a polygon has, the more incredibly complex the number of possible dissections becomes.
Yeah, it's kind of mind-boggling when you think about it.
Yeah, it's like it makes intuitive sense, but it's fascinating to see it actually laid out in a formula.
Right, and this is where things start to get really interesting, because now we can start connecting this seemingly abstract sequence to real-world problems.
Well, that's what I was wondering. Does knowing the number of ways to dissect a polygon have any practical applications?
It does think about computer graphics, for example. When you're rendering complex shapes on a computer, you often need to break those shapes down into simpler ones for processing.
Okay.
And triangulation, which is essentially what we're talking about here. It's a very common technique in computer graphics.
So understanding the number of possible triangulations and how that number grows could be useful in optimizing those processes.
Absolutely. It could help make things more efficient.
Wow. And what about other areas? Are there other places where this comes up?
Yeah, definitely. Map making, for instance, often involves dividing regions into triangles for calculations and analysis.
Okay.
And even something like origami, the art of paper folding,
Oh, wow.
that relies on strategic dissections to create intricate designs.
So this seemingly abstract mathematical concept has its fingers in all sorts of practical pies.
Exactly. You never know where math is going to pop up.
It's amazing. It really highlights how valuable exploring these OEIS sequences can be.
It really does. It's a testament to the power of pure mathematics. Sometimes the most abstract ideas end up having the most concrete applications.
So there's always something more to discover.
Always.
So we've gone from dissecting polygons to Catalan numbers to generating functions and even to applications in computer graphics and map making. Is there anything else hiding in this sequence?
Well, there's always something more to discover with OEIS.
I bet there is.
And remember those BIC paths we talked about earlier? Well, there's another fascinating connection between those DIC paths and A000150
Okay.
that involves something called Linden words.
Linden words. I'm not familiar with those.
Yeah, so a Linden word, it's basically a string of characters that's lexicographically smaller than all of its rotations.
Okay, so what does that mean? Give me an example.
Sure, so the word cat is a Linden word
Yeah.
because it comes before Ithaca and Atra in the dictionary.
Okay, I see. So how do these Linden words fit into our dissection puzzle?
Well, it turns out the number of rooted asymmetric dissections of an n-gon is also equal to the number of Linden words of length 2 cent with certain properties.
So the structure of these special Linden words somehow mirrors the way we dissect polygons.
Exactly. It's like these two seemingly unrelated concepts are just two sides of the same coin.
It's incredible how these connections just keep popping up.
It really is. And this connection is actually highlighted in the OEIS by a cross-reference to sequence A051168,
Okay.
which deals with counting these special Linden words, and A000150. It's actually a diagonal of a square array that's described in A051168.
It's like we're pulling on a thread and this whole tapestry of mathematical concepts is unraveling.
That's a great way to put it, and it really is the beauty of the OEIS. It's like a treasure map leading us to all these hidden connections.
Well, I think we've successfully dissected sequence A000150.
I think so.
We've explored its definition, its connections to dig paths, binary trees, Catalan numbers, even Linden words. We delved into its formulas and growth, and we even uncovered some real-world applications.
Yeah, it's been quite a journey.
It has, and to our listeners out there, I encourage you to explore the OEIS for yourselves.
Yeah, definitely.
You never know what mathematical treasures you might uncover.
Absolutely. And as you dive into these sequences, just remember, the journey is just as important as the destination.
That's a good point.
Enjoy that process of discovery, those aha moments, and just the sheer beauty of the interconnectedness of mathematics.
Well said. Thanks for joining us on this deep dive into the fascinating world of A000150. Until next time, happy exploring.